All right. Good day, everyone. Good evening to Nigerians. Good morning to those who experience morning at this time. Good afternoon to those who also experience their noon by this time. Welcome to day one of our 10 days intensive training on solar PV system design using ETAP software. And this training is organized by JP Smart Solutions Ltd. All right, so my name is Ekwe Jesse, and I'll be your facilitator throughout this training. It's great to actually have you all here today. This session marks the beginning of a practical and knowledge-packed journey into solar PV system design, from understanding core concepts to simulating and analyzing complete systems on ETAP software. As earlier stated, today's class is completely free, but it also gives you a preview of what's coming in the rest of the training. So if you find today's session valuable, and of course I'm sure you will, you can register to continue with us through the remaining 9 days of in-depth learning and practical design sessions. So right now I'll be giving a quick overview of what we'll be covering in this training. So the first outline, we have the Module 1 to Introduction to Solar PV Systems, and Module 2, Solar Radiation and Solar Irradiation, Module 3 for Solar Panels, Module 4 for Reference Standards in Solar PV Systems, Module 5 for Introduction to ETAP Software, which we'll be using for the design. Module 6, we are going to talk about on-grid, off-grid, and hybrid solar systems. Module 7 will be carrying out the design of an on-grid solar system, and that brings us to the end of the training, which we are going to issue certificates. So I'm going to give a more detailed outline from our training syllabus. All right, so we have the intensive training on solar PV system design using ETAP software. So this part is for who should attend this training. If you are yet to get the syllabus, you can easily reach out to us and we will share the syllabus to you via WhatsApp or your email. So this training has a primary objective of equipping participants with the knowledge and practical skills required to design safe, efficient, and reliable solar PV systems using industry standards and, of course, ETAP software. So as we said, we are going to be giving a more detailed outline of the training. And in Module 1, which we are going to begin today, we are going to be talking about the concept of solar PV systems, the components of solar PV systems, the categories of solar PV systems, and of course, we are going to be talking about a very important section, which is solar system design angles, where we have the declination angle, the elevation angle, and the tilt angle. So once we are done with that, we can proceed on to Module 2, which we mentioned earlier as solar radiation and solar irradiation. So we are just going to be talking about the concept of solar radiation and solar irradiation, as well as the types of solar irradiation. Then we move on to Module 3. Of course, we have to know what solar panels are all about. We talk about the characteristics of solar panels. We talk about the tests applied on solar panels, the standard test conditions, and the NOCT tests. We talk about the factors affecting performance of solar panels, system and installation factors. Remember, this training is not just for the design. It will guide you both on the design, installation, and maintenance of solar panels. Once we are done with Module 3, we move on to Module 4. Designing solar panels is not complete without following adequate standards. So we are going to be talking about reference standards in solar PV systems, IEC standards, we have a whole lot of them, ISO standards, we have regional and national standards such as the IEEE standards. We also have codes of practice such as the NEC, and we are going to explain the relevance of following these standards while designing your solar PV systems. And of course, we mentioned we are going to be using a software known as ETAP software for this design. So of course, we need to teach you about the software. So we are going to introduce you to the software in Module 5. Over here, we have the concept of ETAP software, the overview of ETAP software, the capabilities of ETAP software, how to model a single line diagram using ETAP software, how to carry out a powerful analysis using ETAP software. Just a quick preview, this is the software we are talking about here. So we can use it to model our PV system here, which would export data and power to the grid. So we have a meter here for monitoring whatever is flowing to the power grid. So this is a preview of the software, which is ETAP version 24.0.1. And no need to worry, as long as you're registered for the training, we will also be giving you the software. Yeah, most of you who are really into power system design, analysis, optimization, and protection must have come across the software, ETAP software, and you know what the worth of version 24 is at the moment. But we'll be giving it to you totally free once you register for this training, because we believe in hands-on exercise. So you're also going to be carrying out the design of a solar PV system using the software. So once we are done with this introduction of the software, we move on to module 6, which is the on-grid, off-grid, and hybrid solar systems. So we are going to talk about the concept of on-grid solar systems, concept of off-grid, and the concept of hybrid solar systems. And with that existing knowledge, we can now move into module 7, the design of an on-grid solar system. So this is the main hands-on exercise we are going to be having. And in this section, we are going to be looking at solar panel design calculations, inverter selection and settings, then simulation of the designed PV system. So the software not only allows us to design the system, it also allows us to simulate, to understand how it exists, how the system behaves under power scenarios. So we'll be looking at all that, and we have some benefits over here for registering for this training. We have the free installation of ETAP software version 24, hands-on ETAP design experience, global and local solar standards, certificate of completion, master off-grid, on-grid, and hybrid systems. Of course, you save cost with proper system sizing, and it will also boost your career and business opportunities. Alright, at this moment we are about to begin. If you can hear me, kindly give a thumbs up so we proceed. Can anyone hear me? Kindly give a thumbs up. Okay. Alright, today we are going to begin the training as earlier stated, and we'll be covering the fundamentals of solar PV systems. So we are going to be talking about module 1, introduction to solar PV systems, the concept of solar PV systems, components of solar PV systems, categories of solar PV systems, and of course the solar system design angles. So we have the declination angle, the elevation angle, and the tilt angle. So let's move back to our PowerPoint and concept of solar PV systems. So the first question that comes up is, what is a solar PV system? Now, a solar PV system, PV is just an acronym for photovoltaic. So a solar photovoltaic system is one which converts sunlight into electricity using solar panels. Yes, it doesn't have to be complex. Just converting sunlight to electricity using solar panels. So these panels actually generate direct current, DC. So it produces DC electricity, which is then converted into AC current, that is alternating current, by the use of inverters, so that we can use it in our homes, industries, or export to the grid, which is all about on-grid solar systems. So in simple terms, the sunlight sends power to the solar panels, which receives it in DC power. And when we receive this DC power using our solar panels, we make use of what we call the inverter, which converts the DC direct current to AC alternating current. And this alternating current is what we can actually use in our homes, industries, or we can export to the grid. Yes, it's as simple as that. It doesn't need to be complex. So, at this point, we are going to be moving into components of solar PV systems. Now, the first important component we need is the solar panels, also known as photovoltaic modules. And the function of solar panels is to convert sunlight into DC electricity using photovoltaic cells, as we mentioned earlier. And we have various types of solar panels. The first is which we have here, which is the monocrystalline panel. It has high efficiency. It has a compact size. However, the cost of this is much more higher compared to the other types of solar panels. And it is actually easy to identify. We have a picture here. Now, this is the picture of a monocrystalline solar panel. We are going to be comparing it with the others to see how we can identify it. So remember the qualities. The efficiency is quite high. It has a compact size. However, the cost is higher. The next solar panel we have the polycrystalline. Now, the efficiency is quite moderate compared to the monocrystalline. However, it is much more affordable than the monocrystalline. And a graphical representation is this. So we can see that in the monocrystalline, there are some diamond shapes in the panel design that easily aids identification by visualization. So by looking at it, we are able to tell the difference between both panels. The next type of solar panel we have is known as the thin film solar panel. So we have this guy, the thin film solar panel. Now this one is much more flexible, and in weight it is light. It is a lightweight solar panel. However, the efficiency is much more lower compared to the others. And how does it look? It's quite flexible. It's foldable, as you can see. This is the visualization of the thin film solar panel. So compared to the three, it has the lowest efficiency, it is lightweight, and it's flexible. So in terms of where we do not have a structure for the solar panel, this is much more advisable. However, take into account lower efficiency. So the first component we need for a solar PV system is, of course, the solar panels. Next, we require charge controllers. So what is the function of a charge controller? Basically, a charge controller regulates the power coming from solar panels to the battery. So it prevents overcharging and over discharging. We practically have two types of charge controllers. The first is the pulse width modulation, which we have on the screen. The second is the maximum power point tracking, MPPT. Now, the difference between both is that the pulse width modulation is much more affordable and suitable for small systems. Emphasis on small systems. However, the MPPT, which is the maximum power point tracking, is a more advanced charge controller, which extracts maximum power rather, and it is much more ideal for larger systems. Now, it is important to note that in some solar PV systems arrangements, we may skip the charge controller. What I mean is that we may not necessarily need a separate unit for charge controller, and I will explain that as we progress. So the next component we actually require in a solar PV system design is the battery. We need batteries for energy storage. However, it is not in all solar PV system designs that require batteries. You can have a solar PV system without battery. So of course, the function of a battery is to store excess solar energy. And when is this solar energy required? It is required at night or during cloudy periods. So we get sunlight during the day, which powers our homes, our utilities, our industries, whatever equipment we want. And then at night, when we no longer have the solar power to power it, we can then rely on the batteries because the batteries will charge during the day. So we are using the batteries at night. We have primarily two types of batteries, which are the lead acid battery and the lithium ion battery. Now, in comparison to both, the lithium ion is much more higher in efficiency in lifespan compared to the lead acid. However, in terms of affordability, the lead acid is much more preferable. But of course, we look at efficiency to cost. This is the primary reason a lot of persons prefer lithium ion batteries to lead acid batteries in solar PV systems. The next component we have is the inverter, a very important section. Now, the function of this inverter is basically to convert the DC electricity from either the panel or the battery into AC electricity, because our appliances in our industries, in our homes, use AC electricity. Earlier on, I mentioned that charge controllers may be phased out of the design stage, and this is because we have inverters known as hybrid inverters, which actually have inbuilt charge controllers in them. So if they have the inbuilt charge controllers, there is no need getting a separate unit for charge controllers. So the function of the inverter is basically to convert your DC electricity to AC electricity, be it during the day or during the night. At night, the battery supplies DC to the inverter, which converts it to AC and sends to your appliances. During the day, the solar panel supplies DC to your inverter, and the inverter converts to AC and supplies to your appliances. So we have practically two types of inverters. We can expand them, but basically we have two. The first is the pure sine wave, and the second is the modified sine wave. Now, the difference between both is that the pure sine wave gives you a clean power, which is safe for sensitive electronics. So the pure sine wave actually removes harmonics, which are distortions in your current waveform. The modified sine wave is cheaper but less efficient. So while taking into consideration the inverter, it is important to note that the size of the inverter in kilowatts must either match or exceed the system load demand. It is always preferable that it exceeds the system load demand. So these are the major components of solar PV systems. Next, we are going to be moving into categories of solar PV systems. And basically, we have two categories. The first is rooftop PV systems, which means that they are mounted on the roof of buildings, as the name implies. And this is basically a range of 10 kilowatts to 100 kilowatts. 10 kilowatts to 100 kilowatts. And this means that they are mounted on buildings as earlier stated. The second category is the utility scale PV plants. Utility scale PV plants. And this is for 1 megawatts and above. And in this case, we are talking about large ground-mounted solar farms. Now, it doesn't necessarily mean it must be on the ground. It can be on a platform. We have solar farms on oceans. So, but the idea is that it is a solar farm and it is large. We can't have a solar farm on a roof. So these are basically the two categories of solar PV systems we have. Any questions so far? We are about to move into the solar system design angles. So we can take questions on this before we go into that. Any questions so far? Okay. In the absence of questions, we can proceed into the Alright. Solar system design angles. So the first angle we are going to talk about is known as the declination angle. Now the declination angle is the angle basically between the rays of the sun and the plane of the Earth's equator. Okay, I think we have a question. Okay, I think the microphones are muted, so let me give access to that. Okay. Alright, so your microphone is enabled now. You can ask your question. Mr. Augustine, you raised the hand. Okay, we can proceed. Alright, so we are talking about the declination angle. And we say the declination angle is the angle between the rays of the sun and the plane of the Earth's equator. So what we mean is, this is the Earth, and we have the equator. So the rays of the sun coming from this direction, crossing the Earth's equator, forms this angle, which is the declination angle. Now, this declination angle changes throughout the year because the Earth's axis is actually tilted about 23.45 degrees. So it tells us how far north or south the sun is relative to the equator on a given day. How do we calculate this declination angle? We have this formula over here where we have the declination angle is equal to 23.45 degrees multiplied by the sine of this 360 over 365 multiplied by 284 plus n, where n is equivalent to the day of the year. For example, January 1st is equal to 1 and December 31st is equal to 365. So depending on the day of the year, we can factor in the n value and, uh, and obtain our declination angle. All right. So next we have on March 21st. Now on March 21st, which is spring, this is the Earth's equator, and this declination angle will be similar to the Earth's equator, which will make it at 0 degrees. So at 0 degrees, the day's hours, the number of hours during the day is equivalent to the number of hours during the night, because the sun is directly above the equator. So this means that the earth is aligned exactly with the center of the universe. Then we have June 21st, which is summer. In this case, we have plus 23.45 degrees as our declination angle. So what we are saying here is that we have this value when the earth moves anti-clockwise around the sun. So its declination angle increases from 0 to its maximum value of 23.45 degrees. And in this condition, the day hours is much more greater than the night hours. This explains why we can have longer day and shorter nights, or longer nights and shorter day. Now, during autumn, on September 21st, the declination angle goes back to 0 degrees just as this. And the day hours is equivalent to the night hours, of course, because it is 0 degrees. And then during winter, we have declination angle of negative 23.45 degrees. And of course, it becomes the reverse of summer, because the day hours is less than the night hours. Now, let me explain that using this diagram. Firstly, we have the declination angle at 0 degrees, which means the rays of this sun is directly above and aligned with this line here. So there is no difference in angle. And in such a scenario, we are saying that the day hours is equivalent to the night hours. Then we have the summer, which occurs on June 21st. And we are saying that that occurs when the earth moves in an anti-clockwise direction around the sun. So if we are going anti-clockwise, it means we are coming over to this side. So if we are getting the sun rays from this direction, we have a maximum angle of 23.45 degrees. So at this point, when the sun rays are coming from this direction, the day hours is going to be larger than the night hours. We are going to have a declination angle of 23.45 degrees. And then while still moving anti-clockwise, we come back to the equator again, which gives us a declination angle of 0 degrees. So in that case, we are at autumn, September 21st. And the day hours again will be equivalent to the night hours, because the Earth's axis aligns with the universe axis, which is also aligned with the ray of the sun. So while moving anti-clockwise, we now move to this direction, the sun rays coming. So remember, we started from this position, we moved over here, and we came down here, and we come back to the original position, which this diagram is, where we have negative minus 23.45. So in this condition, the day hours is lesser than the night hours. So when we say the day hours is lesser than the night hours, we are also saying that the area of the Earth's surface receiving the sun rays will be smaller than the area that is dark. So finally, the Earth will move back to spring, and the cycle continues over and over again. I think someone raised their hand. All right, a quick recap of the declination angle. So we say during the spring, the declination angle is 0, which means that the day hours is equivalent to the night hours. And during summer, the declination angle is positive 23.45 degrees, which means that the day hours is greater than the night hours. And then on September 21st, which is autumn, the declination angle goes back to 0 degrees, which means that the day hours will also be equivalent to the night hours. And then on December 21st, which is winter, the declination angle goes to negative 23.45 degrees, which means that the day hours is less than the night hours. So let me explain that once again using this diagram. All right. Now we have this as the Earth and we have this as the equator. So with this as the Earth and this as the equator, we are going to be using this illustration for spring, summer, autumn, and winter. Now what we are saying is the Earth moves in an anti-clockwise direction, and in the first scenario, which is spring, where we have the declination angle as 0. So what we are saying is that the declination angle, which is the sun, the rays of the sun is directly above the Earth's equator. So the rays align with the Earth's equator. And in this condition, the day hours are equivalent to the night hours. It is known as the spring. The next condition we have is the summer, where we have positive 23.45 degrees on June 21st. So we say the Earth moves anti-clockwise around the sun. So its declination angle increases from 0 to a maximum value of 23.45 degrees, which means anti-clockwise, the rays of the sun coming from this direction, until we have a maximum declination angle of 23.45 degrees. And in this condition, the day hours becomes larger than the night hours. Then it rotates up till this point where the sun becomes aligned with this equator again, that is autumn, on September 21st. So at that point, the declination angle becomes 0 degrees again, because once the sun rays is aligned with this guy, the declination angle becomes 0 degrees. There is no distance between the rays of the sun and the equator. So once again, in such a condition, the day hours will be equivalent to the night hours. And finally, we have this, which is the original diagram. We have this condition on December 21st, which is winter. Now, in this case, the declination angle is equivalent to negative 23.45 degrees. And it is basically a reverse of the summer condition, because the number of hours during the day is lesser than the number of hours during the night. And the area of the Earth's surface, which is receiving these sun rays, will be smaller than the area that is dark. So once we are done with this cycle, then the Earth moves back to spring and the cycle continues between spring, summer, autumn, and winter. And it keeps on going on and on in that cycle. So when designing PV solar systems, the number of hours that we can get solar radiation is crucial, and that gives rise to the need of this declination angle. So we are going to take an example over here, how to obtain the declination angle. So we want to get the declination angle for April 15th. Now April 15th is day 105, and I'm going to show you how to get that. All we need to do is substitute this 105 into the formula we earlier stated for declination angle. Now, this becomes our N 105, and we get our declination angle as 11.5 degrees. Now, how were we able to realize that April 15th is day 105? Now, we know that January has 31 days, February has 28 days, unless it's a leap year, then we have 29. So we're assuming it's not a leap year. And then March also has 31 days. And we are saying 15 days from April. So if we take the sum of all these, 31 plus 28 plus 31 plus 15, it gives us a total of 105 days. And that's how we get 105 here, and the 105 as April 15th. So it is important to note that when we have 23.45 being positive, we have the largest solar hours and we have the largest output power. But when we have the declination angle to be negative 23.45, we have the lowest solar hours and the lowest output power. Now the reason for that is, during the positive declination angle of 23.45, we are at summer. And we said that summer occurs when the earth moves anti-clockwise. And during summer, the number of hours during the day is larger than the number of hours during the night. So the larger the solar hours, the larger the output power. During winter, we have the reverse because the declination angle becomes negative 23.45 degrees. So it means that we have lower solar hours, which produces the lowest output power, because we said that during winter, the area of the earth's surface receiving the sun rays will be smaller than the area that is dark. So this is basically how to get the declination angle while carrying out your solar PV system design. Any questions so far? I'm going to unmute the microphones now. Okay, so any question now? We are about to proceed to the elevation angle. All right, in the absence of questions, we can proceed. Elevation angle. Now, what is the elevation angle? It is important to note that the elevation angle is also known as the solar altitude angle, and it is the angle of the sun above the horizon at a specific time and location. So practically, the elevation angle tells us how high the sun appears in the sky. And this affects shadows and solar panel exposure. So it is basically the angle between the sun rays and the horizontal plane of the earth, which is the latitude. So how do we get the elevation angle? We look at what we call solar noon, which is during midday. Now at solar noon, alpha here, which is representing elevation angle, is equal to 90 degrees minus, this is the latitude of the location, while this is the declination angle. So I think I put that here. This gives us the declination angle, while this gives us the latitude of the location. So your location is very much important while designing your solar PV systems. It is important to note that the elevation angle ranges from 0 degrees to 90 degrees. This is the maximum value. And this is because the Earth orbits about the Sun. So at the moment of sunrise, the sun ray will be parallel to the latitude of that point, and the elevation angle will be 0 degrees. So when the sun is vertical, that is directly above the location, the elevation angle will become 90 degrees. The next solar angle we have is known as the tilt angle. Now, what is a tilt angle? The tilt angle is basically the angle between the solar panel surface and the horizontal ground or plane. Why do we need this tilt angle? We need it to be optimized to ensure maximum solar capture. Tilt angle is just telling us how your solar panel should face. So the tilt angle actually depends on latitude, it depends on season, it depends on the system purpose. By system purpose, we mean summer optimization, winter optimization, or year-round optimization. That is regardless of the season. For year-round optimization, it is usually important that the tilt angle, which is denoted by beta over here, should be equivalent to the latitude of the location. Panels tilted at latitude angle receive maximum annual radiation from the sun. Now, when it comes to solar panel installations, we have new emerging technologies which use what we call solar tracking systems. So what these tracking systems do is to adjust the tilt angle daily or seasonally for better yield. For the northern hemisphere, the solar panel should face south. What we mean is that the panel must face the equator. And then for southern hemisphere, reverse is the case. The solar panels should face north because the panel must face the equator. So if the solar panel is at the equator, then the tilt angle becomes 0 degrees because the sun rays are parallel to the equator. Remember, we said beta is equivalent to the tilt angle. And the next part we are going to be looking at is solar radiation and irradiation. Any questions so far before we move into that? Kindly give a thumbs up if you can hear me. Okay, I think we are out of time already. Okay, Mr. Defemi Jacobs, you have a question?
Oh, oh no, you said thumbs up, so it was a thumbs up, not a question. Sorry.
All right, all right, no problem about that. All right, so any question before we proceed, or I think we would most likely stop here. Or any questions so far?
Yes. Hello.
Hello. Yes, I can hear you.
Yeah, please. Maybe a little more expansion on this definition angle. I know for the four seasons we have the figures, the maximum being plus 3.45. But what happens during the period between those seasons?
Okay, so when we have the magnitude as positive 23.45 degrees, we are saying that we
Mm,
have larger solar hours. So
yeah.
this occurs during summer, which is from that June
Mm,
21st.
Yes.
What happens is that
Okay.
the number of hours during the day becomes larger than the number of hours during the night. And that's why we have larger solar
Mm.
hours. And when we have larger
Okay.
solar hours, we are going to have, of course, larger output power because we are getting more
Mm.
solar power from the sun. The reverse
Yes.
is the case when we are having negative 23.45 degrees because we are going to be having
Mm.
lower solar hours. And why we are having that is because the number of hours during the day is lesser than the number of hours during the night. So we have more night hours,
Yes.
less day hours. So in such a
Okay.
scenario, we don't have much solar power coming from the sun, so we will have lower output power.
Thank you.
If that explains.
Yeah, it's better. Yeah, I got it. Thank you so much.
All right, you're welcome. Any other question? Okay, Mr. Augustine, your hand is up. Do you have a question? Okay. In the absence of questions, let's see how far we've gone. All right, so we've been able to cover module one over here, and next we'll be moving into module two, which is solar radiation and solar irradiation. For the benefit of those who missed out a few parts, the session we are having at the moment is being recorded and will be uploaded on our YouTube channel. For those who do not know the YouTube channel, I'm going to share my screen as I open it. Okay,
Yeah.
so you can easily see our channel. All right, so this is our channel, JP Smart Solutions Limited, where we are going to be uploading the video immediately after the session. And for those who registered with their emails, of course, the links will be shared to you via email so you can watch after it's uploaded. You can also do multiple training on power system design, analysis, and optimization here. All right. So that's that. We have about 10 minutes. Okay, let's see. Maybe we can move into solar radiation. Just continue in our session tomorrow. All right. So we said that solar radiation is the instantaneous power per unit area received from the sun. The instantaneous power per unit area received from the sun, and its unit is now. Okay, before we go there, let me explain in details. For example, on a sunny day at noon, for those in Nigeria, Abuja may record about 950. The difference between solar radiation and solar irradiation, take note of this. Solar radiation and solar irradiation, people confuse this a lot. Solar radiation, we're talking about instantaneous power. Solar irradiation, we are talking about cumulative solar energy over a period of time. This is watt per meter square. This is watt hour per meter square. So once we are introducing the time factor, we are talking about solar irradiation. It is for this reason solar irradiation is much more important than solar radiation because the longer solar hours we have, the more output power we get. So this is the basic difference between solar radiation and solar irradiation. Now, in our training tomorrow, we are going to explore in details the type of solar irradiation such as the direct, diffuse, and global horizontal irradiation. And as we said, we would be going into that in details over here. So the types of solar radiation. Then we proceed to solar panels. We've talked a bit on solar panels today, where we had the types of solar panels and easily how to identify them just by visualization. So we have the monocrystalline, the polycrystalline, and the thin film solar panels, where we also highlighted the advantages and disadvantages compared to each other. So tomorrow's session, we are briefly going to explain the types of solar irradiation and then move on to solar panels in details. What they are, their characteristics, how to properly select a solar panel, the tests applied on a solar panel to verify that this solar panel is good enough. Then we are going to talk about some issues affecting the performance of solar panels. Why would you have a 50-watt solar panel and it is producing 100 watts of power? We are going to be talking about. We are also going to be talking about some of the problems people face while installing solar panels. So we are going to address that and how to solve those problems. So at this point, we have come to the end of the session. Any questions so far before we call it a day? Remember, from tomorrow, the sessions are no longer free. It is restricted to those who have enrolled. And we quite have a limited number of participants required for each session. So it's basically on a principle of first come, first serve. So the earlier you register, the better for you. Any question before we end today's session? Question, contribution, suggestions, we are open to all.
Yeah, excuse me, facilitator.
Okay.
Like you said, these lectures we posted on the YouTube panel.
Yes, this particular one for today will be posted there.
Okay,
So everyone,
okay,
because today's session is free, so it's open for all.
okay,
But some of
okay,
the lectures will not be posted for everyone, only to those who register.
okay. All right. Thank you so much.
All right. Any other question?
Please, when you share it, please share it on IEEE Nigerian section group so we can know the YouTube link. Thank you for a wonderful lecture. I joined late, so I would like to watch again, please.
All right.
Well done.
No problem. Thank you so much. Any other question or contribution?
Please, what's the registration link? What is the registration link, please?
Right. So for those who wish to register, they can just send us a message on WhatsApp using this, or better still, drop your WhatsApp contact in the chat, and my team would reach out to you and guide you through the registration process. You can either contact us using these details or a drop your WhatsApp number in the chat or your email, and my team will contact you as soon as possible. Okay. All right. Once again, thank you all so much for joining in on today's session, and we hope to see you in other sessions coming further. Do enjoy the rest of your day. Remain JP Smart Solutions Ltd.
Thank you so much. Have a wonderful evening too.